Hi everyone, welcome to the fifth video of STAT 248, couplings and Monte Carlo. This is about convergence rates of Markov chains. So we are starting the third chapter of the lecture notes. And in this chapter, we will look at the rate of convergence of the Markov chains generated by MCMC algorithms to the stationary distributions. So we've talked about MCMC in chapter 1. In chapter 2, we looked at distances between distributions, such as total variation and Wasserstein distances. And here we're going to combine those ingredients to study the distance from the Markov chains to the stationary distribution, either in the total variation or the Wasserstein distance. So far in the course, we've looked at, in the first chapter, Markov chain Monte Carlo methods, as well as other Monte Carlo methods. But Markov chain Monte Carlo methods were a generic way of obtaining a sample from a distribution pi by generating a Markov chain started from a distribution pi 0 and iteratively generating xt given xt minus 1 from a Markov transition kernel denoted by k. And so the design of the algorithm that translates into the design of the kernel is such that we hope, or the goal of this is that the Markov chain xt would eventually converge to the target distribution pi of interest. And for example, this might occur because we design a Metropolis Hastings algorithm or a Gibbs sampler or a Hamiltonian Monte Carlo algorithm, for example, in such a way that the Markov kernel is pi invariant, or we design it in fact so that it's reversible with respect to pi, which implies pi invariance. And so we hope that convergence will follow. And meanwhile, in chapter 2, we've looked at different notions of distances on the space of probability distributions. One of them was the total variation distance and its relationship with maximal couplings. Another one was the optimal transport distance or Wasserstein distance related to common random numbers coupling in the case of one-dimensional distribution. So in the next chapter, chapter 3, starting from this video, we'll measure the distance between the stationary distribution and the Markov chain at step t. So the distance from xt to its limiting and stationary distribution, denoted by pi. And we're going to measure that distance in total variation or using the Wasserstein distance. And so for that, we'll use couplings of Markov chains this time. So we're going to introduce pairs of Markov chains designed in a particular way so that we can measure the distance between their marginal distributions. So the overarching goal of this chapter is the quantification of the rate of convergence of a Markov chain Monte Carlo algorithm. That is the rate of convergence of the generated chain to its limit. So we'll be talking about convergence of MCMC algorithms. We'll denote by pi t the distribution of xt, the Markov chain, at step t. So having evolved from x0 over t steps. And we'll call pi t the marginal distribution of the chain at time t, or step t. This marginal distribution can be defined recursively, where the recursion writes pi t as an integral of pi t minus 1 multiplied by k. And that's integrated over xt minus 1. So this integral is not often tractable, but we can at least write it in the form of an integral. We cannot often compute exactly what pi t might be. Perhaps an exception is the case of discrete spaces, where this can be written pi t equal pi t minus 1 times k, where pi t and pi t minus 1 are row vectors, and k is a matrix, the transition matrix. So in that case, the recursion is a bit more explicit. So what we might want to obtain in order to understand the convergence of the algorithms is the rate of convergence of pi t to the stationary distribution pi. And in order to quantify this rate of convergence, we'll introduce a distance between pi t and pi, and that can be the total variation distance, that could be the Wasserstein distance, of course, any other distances, and so the literature sometimes employs the Kullback-Leibler, the chi-square divergence, and so on and so forth. So to be more explicit about what is meant by a rate of convergence, for concreteness, we might prove, for example, that the distance between pi t and pi is less than a function f of t, where f is a decreasing function, so that f of t goes to 0 as t goes to infinity. And then f of t can be called the rate of convergence. So for example, we'll often have that pi t minus pi, it will be less than a constant c times rho to the power t, where c is a finite constant and rho is a value between 0 and 1. In that case, we will say that we have geometric ergodicity. The Markov chain is geometrically ergodic. So it converges to the stationary distribution geometrically fast. And in that case, we might call the rate rho, or we might call rho, the value between 0 and 1, the rate of convergence. And we might want to know a bit more about this rate, for example, how it depends on important feature of the target distribution, such as the dimension, or in any context, we might have some specific aspects of the target that we might want to understand the effect of. So there are other types of convergence than geometric ergodicity. For example, sometimes the chains converge slower than geometrically in the form of the rate. For example, polynomially, when the distance is less than c times tau, times t to the power minus k. This is meant to be a t on the right-hand side, where k is a positive value. So then we say that the algorithm is polynomially ergodic. And this is more rare in the context of MCMC, but it exists. There are notorious algorithms that deliver chains that converge only polynomially. For example, the pseudo-marginal algorithm. Now, when I say slow or fast, here it's not clear. Like you can have a fast chain converging polynomially and a slow chain converging geometrically. So the dichotomy is a bit more complicated than that. Now, of course, you might also be interested in the convergence of averages. So for example, 1 over t sum of h of xt. You want this to converge to pi of h, which is the integral of h with respect to pi, the integral of h of x pi dx, as a capital T goes to infinity. So that's a law of large numbers, or an ergodic theorem, as it's called sometimes in the study of Markov chains. And furthermore, on top of a law of large number, you might want to have a central limit theorem. So a central limit theorem is something of the form square root of t times the average minus the limit pi of h. And that quantity converges towards a normal distribution centered at 0 and with some variance v that depends on k, the Markov kernel, and the function h. So in that case, in that setting, the rate is square root of t, the standard Monte Carlo rate. And what is of interest then is the asymptotic variance. The asymptotic variance will be different depending on the algorithm. And so the study will focus typically on the study of the asymptotic variance. So this is called the central limit theorem. Of course, it's very important. From this central limit theorem, we can construct confidence intervals around the empirical averages. And in that case, again, the focus is often on the asymptotic variance and how the algorithm or the different tuning parameters like step sizes in the algorithm impact the asymptotic variance. But here in this course, we'll focus on the question of convergence of marginals, which is in any case a building block in the study of the convergence of averages, and that we can study quite precisely with coupling methods. So we focus on the convergence of marginals. I'll mention a few references for the problem of convergence of Markov chains. There are many books, articles on the topic, and certain are particularly convenient for people who have Markov chain Monte Carlo methods in mind. In particular, Levin, Perez, and Wilmer, 2009. It's freely available online, called Markov chain and meeting times. Is focusing on the case of discrete state spaces, but it's very clear. There's Roberts and Rosenthal, focusing on the continuous case, continuous state spaces. That's a review article from 2004. And there's a review of article of Mark Jerome in 98, a bit older, but very insightful as well. That one is mostly on discrete state spaces. So first, let's wonder why the marginals would actually converge. It's not obvious that they would converge to pi. As mentioned before, in MCMC, we designed the Markov kernels, denoted by K, via the design of algorithms, in such a way that the Markov kernels are pi invariant. That is, we construct the kernels in such a way that we have the recursion pi equal to pi times k, using the notation of finite state spaces. Or in continuous state spaces, we have that pi of dx is the integral of pi dz k of z dx over z. So that's a sort of a fixed point type of property. But of course, we don't start at stationarity. We start at pi 0. And we iteratively generate the chain so that it follows successively pi 0, pi 1, pi 2, and so on. And so at time 1, it follows pi 1 marginally. And we can write, of course, pi 1 as pi 0 times k. And then we go to pi 2, which is pi 1 times k. And thus it's pi 0 k to the 2. All the way up to pi t, which is pi 0 k to the t. In the case of finite state spaces, it's really the transition matrix k to the power t. Otherwise, it's just a notation for the tth iterate of the Markov chain. And so it takes the form of a fixed point iteration. So it might converge to the fixed point pi under some conditions, but it's not obvious that it would always converge. It would certainly require some additional condition. So we're going to first look at the convergence in a very concrete case, very simple example on a continuous state space using autoregressive processes of order 1. They are defined on a real line by x0 follows a normal centered at mu0 and variance sigma 0 square. And then at all times, t larger than 1, xt is defined as alpha xt minus 1 plus tau epsilon t. And epsilon t are IID normal 0, 1 variables, independent and identically distributed. Then we can work out, in that particular case, the marginal distributions pi t exactly, recursively exactly. So in particular, we can work out by calculation that x1 is normal with mean alpha mu 0 and with variance alpha square sigma 0 square plus tau square. We can likewise compute the mean and the variance of pi 2. And we can recursively obtain the mean and the variance of pi t. And this is alpha to the t mu 0 for the mean, and alpha 2t sigma 0 square plus the ratio 1 minus alpha to the 2t over 1 minus alpha square times tau square. And so we can work out, as t goes to infinity, that the mean goes to 0 and the variance goes to tau square over 1 minus alpha square. And so if we write this normal distribution pi t, it converges to a normal distribution that we can call pi, is the stationary distribution of the process. And so here we just see that the mean and variance converge, and so the whole Gaussian converges because it's characterized by the mean and the variance. But we can also compute very easily here the Kullback-Leibler divergence between pi t and pi, or the Wasserstein 2 distance. Those notions of distances have explicit formulas for the case of Gaussian. And so we can compute them in terms of those means and variances and see that they converge to 0. So we can obtain the ergodicity results exactly because we have access to pi t marginally. So next we can see how more generically we can obtain the convergence of the marginals. And for that we're going to follow theorem 4.9 of this book, Markov chain and mixing times. And that's focusing on the case of discrete finite state spaces. So here, K, the transition kernel, is simply a matrix, say M by M, where M is the size of the state space. We're going to assume that there exists an integer R such that for all states x, y, K to the R from x to y, which is the probability that xr will be equal to y given that x0 is equal to little x, I'm going to assume that it's strictly more than 0. So the chain can go from any x to any y in r steps. And we're going to further assume that k is pi invariant. So we have the equality between pi and pi times k. Then let's prove that pi 0 k to the t, which is the tth marginal of the chain, converges towards pi. So let's prove this. By assumption, there exists a delta larger than 0, such that k to the r is more than delta times pi for all x and y. So that comes from the assumption. And the fact that the state space is finite. And thanks to this, we can write k to the r as a mixture of delta pi plus 1 minus delta times a residual kernel. And we simply write the difference between k to the r and delta pi, renormalized so that it's a Markov kernel. So this quantity on the right-hand side, we can write q of xy, and it's a Markov transition kernel, so it's a matrix with entries at xy, such that for all x, the sum of the entries q of xy sum to 1. So q is a stochastic matrix. So in matrix form, we can rewrite this expression as k to the r is equal to delta times the big matrix pi plus 1 minus delta times q, where the big matrix pi is simply made of rows all equal to the vector pi, the row vector pi. So all the rows of big pi are simply the row vector little pi. So we can check this recursion first, that k to the r to the power n is equal to 1 minus theta to the n times the big matrix pi plus theta to the n q to the n, where here theta is equal to 1 minus delta before. And this can be checked by induction. So what we've just written above is the case where n is equal to 1. And we can check that if it's true for little n, it's true also for n plus 1, by induction. And for that, we simply use two properties. Pi times k is equal to pi. That's the pi invariance of k. And furthermore, q times pi is equal to pi. That's simply because q is a stochastic matrix. And all the rows of big pi are equal to the same vector. So that's because q is stochastic. The rows sum to 1. So that can be used to check the induction. And so then, if we are happy with the claim, we can obtain that k to the power r times n plus some index j minus the big matrix pi is theta to the n times qn p to the j. Oh, sorry, the matrix P here should be the same as the matrix K. It's a typo. Minus pi. And so from that, you can compute the total variation distance between pi 0 times k to the Rn plus j. So that's the marginal distribution at step Rn plus j. And you can compare this to pi. And because the right-hand side has a theta to the n, you find a bound in theta to the n times the total variation distance that you can simply upper bound by 1, because the total variation is always less than 1. And so you find a geometric ergodicity result with a constant rate theta equal to the 1 minus delta, where delta was in the assumption. So the point of this kind of result is that in theory we might be able to state, again, a geometric ergodicity result of this form, so an upper bound on the TV of the form c times rho to the t for some constant c and rho. And so it's meant to be practical in the sense that if we have such results, then we can talk about the mixing time, more precisely the epsilon mixing time, defined as T of epsilon is equal to the infimum over all times such that the distance between pi t and pi is less than epsilon. So T of epsilon is the first time at which the total variation distance between pi t and pi is less than epsilon. And so you'd like to run your algorithm for that time with a small epsilon. And with a bit of calculation, you find, for example, that if you have c rho to the t is less than epsilon, equivalently, you should pick t larger than log epsilon over c divided by log of rho. And you can put minus signs in front of this because both the numerator and the denominator are negative. The logs are negative when epsilon and rho are small. And so then you can get some sort of guideline on the choice of iterations to perform, of course. That's the overarching goal. For example, if you know that the rate rho is less than 1 minus 1 over d, where d is the dimension, for example, then with elementary calculation, for example, log rho is less than minus 1 over d, you find that this would mean your mixing time increases like d times minus log epsilon over c. So for example, if your algorithm is such that the mixing rate rho is less than 1 minus 1 over d, this would suggest that you should run a number of iterations linear in d, whether d represents the number of components in the state space or some way of characterizing the difficulty of the problem. Now, of course, in practice, it's a bit more difficult because the upper bounds that we will get in our geometric ergodicity results will rarely be accurate enough to translate into a concrete guideline. And so, for example, you might know some things about C and rho, the constants in the above inequalities. However, you might not know exactly what values you should take for those constants in practice. And so then, if you don't have exactly the values of C and rho, then you cannot exactly get a mixing time, and so you cannot exactly choose your number of iterations to perform in this way. So those results help at a high level, but not in a specific choice of little t. We will see in the later chapter more concrete tools based on couplings to really specifically choose the number of iterations t to perform. So it's worth emphasizing that the question of convergence in practice, that is, for a real problem using an algorithm on your computer, how many iterations to perform, is a very difficult problem. Why is it so difficult? Because when we run the algorithm, we observe a trajectory of the Markov chain. So we observe one value for x0, x1, all the way to xt. You observe a trace. And each of those x's is one draw, one sample from a different distribution, pi 0, pi 1, pi t. And what we would like to do is to choose little t so that pi t is close to the limiting distribution pi. So that, for example, pi t minus pi in total variation is less than epsilon. But if you think about it, we do not know pi. We do not know much about pi because that's what we're trying to approximate. Secondly, we only have a single draw at each time t. So we only have one draw of the distribution pi t. And furthermore, computing the distance between pi t and pi is generally difficult. Even if we knew a lot of things about pi t and pi, computing the total variation distance between two distributions itself is a difficult problem. So between what we can do, which is sample the trajectory, and what we would like to do, which is finding the mixing time, there's a lot of obstacles. So what do people do in practice? They might do visual diagnostics, so just tracing, plotting many aspects of the chains in order to gather whether they have converged or not at an intuitive level. It's always a good idea to run independent chains so that we can compare the results obtained independently on multiple machines. And so, for example, there's a famous Gell-Mann-Rubin diagnostics that is based on the comparison between ergodic averages obtained on independent chains, called the R-hat diagnostics also, that is often used. We will see in chapter 4 practical application of couplings lead to diagnostics of convergence that are sometimes applicable and provide non-asymptotic diagnostics of convergence. So that will be the topic of chapter 4. So some of the tools that we'll introduce in chapter 3 for theoretical analysis will be reused in chapter 4 to obtain practical diagnostics of convergence. And then another thing that people do in practice is computing confidence intervals. based on their running averages, and deciding to stop the simulations when the width of the confidence intervals is small enough, is reaching a certain threshold. It's not obvious how to do that correctly, but there are also attempts at doing that. Sometimes this is called sequential stopping rules. For example, a paper by Flegal and Gong in 2014 has examples in high-dimensional MCMC settings. So in chapter 3, specifically, we will look at techniques, mathematical techniques, to obtain upper bounds on the convergence rates. So we will try to get those constants c and rho such that pi t minus pi is less than c times rho to the t, where the distance is measured possibly in total variation or in the Wasserstein distance. So the key tool, the focus of this course, of course, is couplings. So we'll see how couplings of Markov chains are going to be used in order to obtain those upper bounds. This is a line of work that originates since the 1930s, so it's an old line of work. And it employs couplings, but also a number of ideas that we haven't seen yet. For example, minorization conditions, drift conditions, contractions, the representation of Markov chains in terms of iterated random functions, and a number of such ideas. And the reason why there are so many ideas is because there are, in a sense, so many Markov chains on continuous or discrete state spaces, Markov chains generated by different types of algorithms. And so there's a plurality of techniques, a diversity of techniques in order to treat a lot of those cases as accurately as possible. So we will see some examples in continuous and discrete state spaces. We've already seen autoregressive processes, and we'll see other random walks. And we'll look also at discrete state spaces that are either finite or infinite. For example, Ising models, the problem of colorings of graphs, for example, the problem of generating subsets of a set uniformly, and so on. So there will be quite a few examples to illustrate those different tools mentioned above, couplings, minorization, drift, and so on. So we will not aim to have the sharpest possible results in this course. So the upper bounds that we will obtain will not necessarily be very sharp. So there might be some sharper results in the literature, but hopefully they will be fairly simple to obtain, fairly intuitive, and still informative. So the upper bounds will not be completely useless. They will, for example, reflect some aspect of the problem in the bounds. So the literature on those kind of topics is very rich. There's a lot of techniques. So here we focus only on the methods based on couplings, which is a small part of the literature. And even within coupling-related methods, we will focus only on a few methods as an introduction to those ideas. But there are hundreds, possibly thousands of articles on the use of couplings to study the convergence of Markov chains. And on top of that, there are other techniques completely different than couplings to study the convergence of Markov chains. For example, the analysis of the spectral gap of the Markov kernel, a technique called conductance that has been successfully applied to a number of Markov chains in the past, and so on. So the couplings is really only one approach among many approaches for the convergence of Markov chains. So one of the objectives of this chapter 3 is to introduce you to this topic, as well as setting the grounds for the methods that are going to be described in chapter 4, and which will employ couplings of Markov chains. We've seen couplings of random variables in chapter 2. but here we will see couplings of Markov chains which we'll be able to simulate later on. For example, in the algorithm called coupling from the past, which is one of the highlights in the chapter 4 to come, that is based on couplings of Markov chains. So let's look at how to obtain convergence rates via couplings of Markov chains. Xt will denote the Markov chain of interest, which starts from the initial distribution pi 0 and is distributed according to pi t at step t. So that's our Markov chain of interest. That's the one we generate on the computer using MCMC to approximately sample from the target distribution pi. And the idea of couplings here is to introduce another chain, a fictitious chain, if you'd like, denoted by yt, which has the same Markov kernel as x, that Markov kernel denoted by k, but it is started from the distribution pi and not from the distribution pi 0. So this chain y is at stationarity. And because k is pi invariant, we have yt following the distribution pi for all times t. Then the total variation distance between pi t and pi, which can be written as the infimum over all couplings xy of pi t and pi, of the probability that x will be different than y. So over all pairs of variables xy with marginals pi t and pi, the TV is equal to the infimum of the probability that x is different than y. And of course, then it's less than the probability that our xt is different than yt, because xt yt as defined above are a particular coupling of those distributions pi t and pi. So because it's a particular coupling, it must achieve more than the infimum. So then we can introduce the meeting time, tau, the infimum, the smallest t, such that xt is equal to yt. So that's the time at which the two chains meet, if it exists, otherwise it's plus infinity. So we're going to assume that there's such a time tau. So if we imagine a visual representation of the chains, we have x and we have y, and they meet. There's a certain time tau, after which xt is equal to yt at all times after the meeting time, as in this figure. And so then the probability that xt is different than yt is the same as the probability that the meeting occurs after time t. Probability that tau is greater than t. So if we put all of that together, we have that the TV between pi t and pi is less than the probability that the meeting time is larger than t. And in the context of Markov chains, this is called the coupling inequality. We've seen a previous coupling inequality, the TV being less than the probability that x is different than y, but in the context of Markov chain, usually the coupling inequality refers to this inequality with a meeting time. And so if that right-hand side goes to 0 as t goes to infinity, then we obtain a rate of convergence in total variation distance of the chain to stationarity. So we obtain an upper bound on the convergence of the chain. So note that in some very special cases, we can imagine that there are processes xt and yt coupled in such a way that the TV between pi t and pi would be exactly the probability that the meeting time is larger than t. So instead of an inequality, we might have an equality. And in such case, we would say that the chains are maximally coupled. So that's, again, in the context of Markov chains, a maximal coupling might refer to the situation where the left-hand side is equal to the right-hand side in this coupling inequality. The pioneering work on this is Griffiths 75 or Goldstein 79, for example, showing examples where maximal couplings in this sense exist. But here we will not, in fact, talk much about those kind of couplings. We will be happy with some upper bounds. So all of the couplings we'll see are going to be submaximal in that sense, suboptimal. Another thing to note in order to perhaps gather some intuition about those probabilities of meeting times being larger than t is that if we have an increasing function such that the expectation of the function of tau is finite, then it implies that this function applied to t times probability that tau is more than t goes to 0. And thus, it would mean that the inverse of the function forms an upper bound as t goes to infinity over the probability that tau is more than t. So if you have this kind of finiteness of the moments of the meeting times, when phi is non-negative and increasing, then phi gives you, phi to the minus 1, in fact, gives you an upper bound on the total variation distance from pi t to pi. So overall, the name of the game here is to couple two chains, the original chain x and the stationary chain y, so that the meeting time has tail probabilities going to 0 as quickly as possible, which will give us a convergence rate as quick as possible. So of course it remains to see whether we can indeed create two chains that meet exactly. So if you look at the meeting time tau as the infimum of the times at which xt is equal to yt, if you recall that the state space in general might be discrete or continuous, it might not be obvious how two chains are ever going to meet. Right? For example, on continuous state spaces, typically independent chains will never meet. And so we'll have to design the chains in particular ways in order for them to possibly meet. So we can look at an example first in discrete state spaces, where it's perhaps less surprising that the two chains might meet. So we're looking exactly at the same example as before, with a Markov transition matrix K, such that in R steps we can go from x to y with positive probability. And thus, as seen before, we can write k to the r as delta times pi plus 1 minus delta times a residual transition matrix Q, which is a stochastic matrix, so its rows sum to 1. And so then we can introduce a coupling between our original chain X and the stationary chain Y. And we're going to imagine the coupling via the way that we sample X and Y over R steps. So they're going to be coupled such that basically to sample the next xt plus r given xt, with probability delta, we sample from pi, and we set yt plus r to be equal to xt plus r. So we're currently at time t and generating what happens at time t plus r. So with the remaining probability, 1 minus delta, we sample xt plus r from q and yt plus r from q as well. One given xt and the other one given yt. And so because of the representation of k to the r above, this is exactly like sampling from k to the r, the original Markov kernel, over r steps. But sampling this way, we have a delta probability of observing a meeting xt plus r equal to yt plus r. So every time we do this r-step transition, we have a delta probability of meeting, and thus the meeting time follows exactly a geometric random variable with success probability delta. So that's a random variable on the integers, such that the probability that tau is more than k times r, the meeting time basically is more than kr for an integer k, is exactly 1 minus delta k, delta to the k. And so all in all, we obtain a geometric rate of convergence, which is exactly the same as we obtained before. But instead of obtaining it by calculating the iterates of the matrix K, we obtain the same rate with a coupling argument, arguably a simpler argument involving fewer calculations. So here we obtain a convergence irrespective of the initial distribution pi 0 in total variation. Beyond total variation bounds, we can also obtain upper bounds on convergence rates in other metrics. So, for example, in the Wasserstein distance. Recall here the definition of the Wasserstein distance between two probability measures, defined as an infimum over all couplings of the expected distance between the two variables to the power k, where k is a value larger than 1, larger or equal to 1. And the whole infimum is to the power 1 over k. So this depends on the choice of distance, d, on the state space, which has to be chosen. And this whole distance is called the Wasserstein distance between the probability measures. So we'll see that with couplings of Markov chains, a bit like before, we can obtain upper bounds on the total the Wasserstein distance between pi t and pi. So we assume that we have our Markov chain xt of interest with marginal distribution pi t, and we have introduced this second chain y, which is at stationarity, so that yt follows pi. Then, by this coupling representation of the Wasserstein distance, we have an inequality with, on the right-hand side, the expected distance between xt and yt to the power k. That provides an upper bound because it's at least the value obtained if we were using the optimal coupling. So we're just using a suboptimal coupling, so we get an upper bound. And thus, if we can create xt and yt in such a way that they contract toward one another, so the expected distance between the two chains goes to 0, they don't have to meet here, just the expected distance goes to 0, then we have an upper bound in the Wasserstein distance of order k. And so visually, we might represent the chains as two traces that go towards one another. So the distance between the two in expectation goes to 0. So they might never meet exactly, but they become very close to one another. So with this technique, we can handle very simply the case of autoregressive processes, for example, in the real line, so on the continuous state space. We can simply introduce a common random numbers coupling. So xt and yt follow the autoregressive recursion, and we give them the same random noise epsilon t at time t. So that's a common random number strategy here. And then we can compute the expected distance between xt and yt using simply the absolute value of the difference as a distance between the chains. And we observe that the difference between the chains will make the noise terms completely disappear. So we're left with alpha times the difference between the chains at the previous time step. And thus, by recursion over the time index, we obtain alpha to the power t times the expected distance at time 0. And so really in two lines, we obtain an upper bound on the distance to stationarity of our autoregressive process with a rate of convergence alpha to the power t. So it converges if alpha is in between -1 and 1, times the expected distance from the initial states x0 and y0. And here I've used a little k equal to 1. So the rate of convergence here is the autoregressive coefficient alpha. So we've seen example of geometric ergodicity results, either autoregressive process or finite state space Markov chains so far, also only very simple cases. But we've looked at results in total variation and in the Wasserstein distance. So that generally is the topic of chapter 3 of the lecture notes, to obtain such geometric ergodicity results. So we can think of geometric ergodicity as the total variation going to 0 geometrically, so very quickly like this. So this looks like it might be less than C rho to the power t. But just to be clear, it could be different. It could look quite different, the total variation distance. So it's always between 0 and 1, but it could start by plateauing from 1 for quite a few steps before it goes down to 0 eventually. In that case, we say that there is a cutoff phenomenon. That's still like compatible with an upper bound of the form C rho to the t, because C might be very large, of course. Right, so in that case, we have a cutoff phenomenon, which has been a very fascinating topic in the convergence of Markov chains. But in this course, we won't look at cutoff phenomena that much. We'll just be happy with an upper bound of the form C rho to the power t. So to obtain those bounds, we'll see more techniques of general interest, such as drift conditions, iterated random functions. And the point of those techniques is to be able to tackle more realistic settings than simply the autoregressive process. Perhaps it'd be nice if we can include some Metropolis Hastings chains or some Gibbs samplers. And so we'll look in particular at some examples like Ising models, how to sample uniformly subsets of a set, or colorings of graphs. Those are classical examples in the study of Markov chains, in particular in the applied probability / combinatorial literature. So this chapter, of course, is about the theory of the convergence rate to Markov chains, of Markov chains to stationarity. But some of the tools that will be introduced in chapter 3 will be also helpful in the next chapter. And the next chapter is really about practical analysis of convergence. So practical tools that users might be able to implement on the computer in order to know how many steps of MCMC to perform. That's it for today. In the next video, we'll continue progressing through the material of chapter 3. And in particular, we'll see more techniques, more theoretical tools for the analysis of Markov chains, eventually, so that we are able to analyze the Markov chains that are generated by realistic MCMC algorithms, not only toy examples such as finite state spaces and autoregressive processes that we've seen so far. So we'll see that next time. In the meantime, have a nice week.